Hello everyone, welcome to the course of Principles of Digital Technique. Today we will see mod and counters. In digital circuit, counters are used to count the number of pulses, as we have seen in synchronous counter and asynchronous counter. First we will see the definition of modulus of a counter. It indicates the number of states through which counter passes during its operation. Suppose I have 2-bit counter, the number of states will be 4. 2 raised to 2 equal to 4. 0, 0, 0, 1, 1, 0 and 1, 1. These are the 4 states. Similarly, for 3-bit counter, we have 2 raised to 3 equal to 8 number of states. So, number of states equal to modulus of a counter. For 2-bit, modulus of a counter is 4. For 3-bit, modulus of a counter is 8. For 4-bit, modulus of a counter is 16 and so on. But what if I want counter which don't belong to this 2 raised to n series? If suppose I want modulus of 3-bit, modulo of 7, then there is the need of modulo counter. Mod n counter is also called as modulo counter. We can design the modulo counter for any number. For example, modulo 3, modulo 5. Design of such modulo counter include the basic structure of a counter which we have seen in synchronous and asynchronous counters, and along with that combinational logic which is called as reset logic is needed to limit the number of states. Number of flip-flops or number of bits to construct the mod n counter is given by this formula: n less than equal to 2 raised to m, where small m is number of flip-flops and n is mod n counter. If suppose I want mod 3 counter, number of flip-flops required will be 2. If suppose I want mod 7 counter, the number of flip-flops will be 3. You can try with different number of mod counters and just check out with the number of flip-flops. We will consider these different steps to follow to design any modulo counter. First we'll see number of states through counter passes. Then we can decide the number of bits for ripple counter or number of flip-flops. Then we can go for state diagram followed by truth table for the reset logic, K-map simplification to get the output equation, and based on that output equation, logic diagram. We will consider one example of modulo 5 ripple asynchronous counter. Ripple means asynchronous. First step to decide the number of states through counter passes. As it is a modulo 5, number of states equal to 5. Those states will go from 0 to 4. So total 5. Then decide the number of bits for your ripple counter by the formula given: 2n less than equal to 2 raised to m. To count 5 states, we need 3-bit ripple counter. Then the third step, state diagram. Total 5 states are given, starting from 0 to 1, 1 to 2, 2 to 3 and 3 to 4. And after 4, our counter will again go to state 0. Truth table for the reset logic. Now, for modulo 5 counter, the valid number of states are only 5, that is 0 to 4. But with the help of 3-bit asynchronous counter, we get total 8 states. So what to do with the remaining states, as these are the invalid states? Hence, we will go for next step. We have to prepare the K-map so that we can get the output equation. The first 5, 0, 1, 2, 3 and 4. For these 4 states, we have entered 1 and the rest 3 are 0. So the upper row is forming one chord and answer will be QC bar, and the first column is forming one pair, that is QB bar into QA bar. So output equation Y is equal to QC bar plus QB bar into QA bar. The last step, that is logic diagram. First of all, we should follow the same structure of counters. We want to prepare asynchronous counter of modulo 5. As it is an asynchronous counter, only to the first flip-flop we will give external clock, and for the rest of flip-flops, the output of previous flip-flop will go as an clock to the next flip-flop. Preset and clear, these are the two active low signals. Preset is kept at logic 1. We need 3 flip-flops, flip-flop A, flip-flop B and flip-flop C to prepare modulo n counter. This is the logic diagram with reset logic, where as from the K-map we have got this equation. So QA bar into QB bar, for that we need AND gate. So here is a QA bar and QB bar indicated with green line, and that are given to the AND gate. Then that is added with the QC bar. So we need OR gate also. So this is added with QC bar. These two are given to the OR gate, and that is the output Y given by blue color line. Output Y is given to the clear pin of all the 3 flip-flops, so that whenever this condition arises, that is, it can be either 5, 6 or 7, counter should automatically reset to the 0 state. So all the invalid states can be easily eliminated with the help of this reset logic. The need of reset logic in the modulo n counter can be cleared from this example. For every modulo counter, you will get different equation for your output Y. Depending on truth table, you can easily write down the equation with the help of K-map simplification. Thank you, and in the next lectures we will go ahead with the different examples. Please solve the assignment questions, and if needed, watch the video again. Thank you.